Have you ever wondered how an AI can look at a bunch of data and just make a prediction? Well, it's not magic. Not at all. It's actually a journey. And today, we're going to follow a single piece of data on its one-way trip through a neural network to see exactly how the thinking happens.
So yeah, that's the big question, right? How does a machine think? You might imagine some kind of super complex, mysterious black box. But the truth is, for a neural network, it's a surprisingly logical, step-by-step process, a one-way trip that we can follow from the very beginning to the very end.
And that's exactly what we're going to do. We're strapping in and following our data on its adventure. This whole process, this journey, it has a name. It's called the forward pass.
All right, so this process is officially known as forward propagation, or as we'll call it, the forward pass. And you should really think of it as the starting line. It's how a network makes its very first guess about anything.
The whole concept boils down to this. It's a one-way street. Your data comes in at the input layer, it flows through these middle sections called hidden layers, and then it spits out a result at the output layer. There's no going back. It's a strict forward-only flow, and that's the key to how a network makes its initial prediction.
Now, to really get this journey, you need to meet the key players. First, you've got your inputs. That's just the raw data we're feeding the machine. Then you have weights. These are like little importance styles on every connection, telling the network how much attention to pay to each piece of input. And finally, you have biases. You can think of a bias as a little head start that makes it just a bit easier for a neuron to get excited and fire off a signal.
Okay, we've met the team. Now let's zoom way in, right down to a single neuron, and see the very first calculation it performs. This is where the numbers start to fly. Inside every single one of these neurons, it's the same simple three-step dance. First, multiply each input by its weight, that importance style. Second, add up all those results. And third, add the neuron's own unique bias, that little head start we were talking about.
Now, theory's great, but seeing the actual numbers makes this so much clearer, right? So let's imagine our neuron gets two signals. Input 1 is 0.1, and its connection has a weight of 0.1. The second input is 0.5, with a weight of 0.3. Let's see what the neuron does with these. So, following our three-step dance, we start by multiplying. We've got 0.1 times 0.1 plus 0.5 times 0.3. That gives us 0.01 plus 0.15 for a grand total of 0.16. See? 2 steps down, just 1 to go.
And for the final piece of the puzzle, we add the bias. Let's say this neuron has a bias of 0.25. So we take our 0.16, we add that 0.25, and we land on our final number, 0.41. And that's it. That's the first part of the neuron's job done. This number, the 0.41, it has a name. It's the weighted sum, and it represents all the incoming information, all boiled down into a single value. But, and this is a big but, this is not the neuron's final output. Nope, it's just the input for the next very crucial step. So after all that math, the neuron has to make a decision. It has to decide, what signal do I pass on to the next guy in line? That is the job of the activation function. It's kind of like a gatekeeper. So why bother with this extra step? What's the big deal? Well, it's all about a fancy word, nonlinearity. And trust me, this is the absolute secret sauce of a neural network. Without it, the network could only learn super simple, straight-line patterns. Nonlinearity is what lets it learn the complex, messy, real-world stuff.
Now, there are a bunch of these activation functions, but here are two of the most popular. You've got sigmoid, which is awesome because it takes any number, big or small, and squishes it into a value between 0 and 1. Perfect for probabilities. Then you've got ReLU, which is incredibly simple. If the number is positive, it lets it through. If it's negative, it just makes it 0. It's super efficient, and it's the go-to choice for most networks these days. Okay, let's get back to our little neuron. It's using that sigmoid function. So we feed it our weighted sum of 0.41, it does its thing, and it spits out about 0.601. And that, my friends, is the final output from this single neuron. That's the signal it's going to pass on. Okay, so we've just seen what one tiny neuron does. Now, you have to imagine this exact same process is happening in every single neuron, all at the same time across the entire network. And this right here is the core idea of it all. It's so simple, but so powerful. The final outputs from one layer of neurons, all those numbers like our 0.601, they just become the new inputs for the very next layer. The information literally flows forward. And so that cycle just keeps repeating. Every neuron in the next layer takes those new signals and does that same two-step dance. Calculate a weighted sum, then apply an activation function. It happens over and over, layer by layer, pushing that data through the system. So, after all this journeying, all this passing from layer to layer, where does it all end up? Well, it all comes together at the final layer of the network, the output layer. This is the finish line, where all these calculations get turned into one final prediction.
You might think the output layer works differently, but here's the cool part. It doesn't. The neurons there, they do the exact same thing. They take the outputs from that last hidden layer, treat them as new inputs, and do the same calculation all over again.
So if we follow our example all the way to the end, after that very last calculation in the output layer, bam, the network gives us its answer. And in this case, that number is 0.734. This is it. This is the result of that entire journey. So what is this number? What does it actually mean? Well, data scientists call it y-hat, and it's basically the network's best guess. So if we were trying to figure out if an email is spam, this 0.734 could mean the network is 73.4% sure that, yeah, that email is definitely spam. So let's just run that back one more time super quick. Data comes in, it travels forward, layer by layer. Each neuron does its little two-step calculation, and it all ends at the output layer with a final prediction. Simple as that.
And that, in a nutshell, is the forward pass. The network took its data, it did the math, and it made its best guess. But that leaves us with a massive hanging question. What if it's dead wrong? What happens when that prediction is way off? How does a machine actually learn from its mistakes? Well, that is a journey for another day.